In this lecture, we're looking at one particular functional group, and that is the ether. The ether is an oxygen atom that's flanked to the right and left with carbon atoms. The ether is a very important functional group and has an interesting and rich history. In Boston, there was a medical surgical amphitheater called the Ether Dome, where doctors would perform surgeries, and ether was used as the anesthetizing agent to make sure that the patient didn't feel any pain. However, ethers are extremely important in organic chemistry, both as solvents, products, and starting materials. In this lecture, we're going to learn a couple ways to make ethers, and we're going to learn about a very special class of ethers called the epoxide. So let's begin with a few ways to make ethers. First, we'll look at the industrial synthesis of simple ether. Most of the reactions we've learned in this course are examples of fine chemical synthesis. Fine chemical synthesis refers to making specific molecules on usually a low scale for the purposes of things like pharmaceuticals or research compounds, things of that nature. However, there's a whole other world of organic chemistry that's based on large scale, go big or go home. This is the home of industrial chemistry. The goal of industrial chemistry is to produce massive amounts of commodity chemicals for as cheap as possible. These sort of reactions are typically conducted in large reactors and use very simple building blocks, things like sulfuric acid and water and methanol. These are all cheap commodity chemicals, and we need to be able to transform them into these massive bulk products that we need in huge quantities, things like precursors for polymers, so plastics, and clothing, textiles, fuels, and also solvents for industrial purposes and lubricants for industrial purposes. And so this reaction that we're going to look at today is pretty much the only industrial reaction that we are going to learn in this class. Almost everything else would fall under the category of fine chemical synthesis. The industrial synthesis of simple ethers begins with a primary alcohol. This is specifically for primary alcohols. The primary alcohol is treated with sulfuric acid and heat. You probably recognize these conditions as the E1 conditions. Okay, so we're going to treat that alcohol with H2SO4 and heat, and the product of the reaction is going to be a symmetric ether. Let's take a look at the mechanism of this transformation. So it all begins with a molecule of ethanol, and remember, it doesn't have to be ethanol. It can be any primary alcohol. And in the first step, the ethanol is going to react with our sulfuric acid. So I'll draw out the structure of sulfuric acid. This is H2SO4, strong acid. And the first step is the alcohol is going to be protonated by that strong acid. That's going to lead to us a protonated alcohol. Now that protonated alcohol is actually going to react with another molecule of ethanol. So another molecule of ethanol is going to come along and do an SN2-like reaction where it's going to attack the alpha carbon and eject H2O as a leaving group. That's going to lead to what is almost the product. It's a protonated ether. And we also generate a byproduct of H2O. Now in the final step, another molecule of the alcohol, you can also show this as a generic base, is going to come along and remove the proton on the protonated ether, push electrons onto that oxygen of the ether atom. That's going to lead to our final product, which is the symmetric ether. Okay. So you can see why this is a valuable industrial process. We're starting with something that's dirt cheap, ethanol, produced a lot of it in America from corn, and then sulfuric acid, which is easily made by the reaction of elemental sulfur, which is mined in huge quantities from the earth when it's combined with water. And we're able to transform those two very cheap components into something that's far more valuable, diethyl ether. We've seen diethyl ether as a common organic solvent. So just some notes for this reaction. It only works for primary alcohols. Because if you try it with secondary or tertiary alcohols, you're going to get predominantly the E1 products, the elimination alkene products, the dehydration of alcohols products. Okay, so that's the industrial synthesis of simple ethers, and this reaction is not very useful. And the reason it's not very useful is if you look at the products, they're symmetric, they're kind of boring. We don't really have much ability to custom fine-tune our reaction. We're very limited. It can only be like methanol, ethanol, propanol, things like that. And so we don't have very much control over making interesting ether. So for that reason, this reaction very rarely shows up on the midterm too. The next reaction, however, is much more powerful, and we've actually seen it already. So this is a review of the Williamson ether synthesis. The Williamson ether synthesis describes a process that is essentially an SN2 reaction. Let's remind ourselves of what that looks like. We would start with an alcohol. It doesn't have to be a primary alcohol, but I'll just draw this as our alcohol. And we treat that with sodium hydride, which is a strong base that's very good at deprotonating alcohols. So that's actually going to rip the proton off of the alcohol and give us deprotonated alcohol, what is called a sodium alkoxide. What's cool about this is the sodium hydride, in effect, supercharges the nucleophilicity of our alcohol. We started off with a very, very poor nucleophile, but after we deprotonated it and put a surplus of electron density on that oxygen, we created a potent nucleophile. Now we use that nucleophile in an SN2 reaction, so we can bring in, for example, an alkyl halide, and now our supernucleophile will attack the alpha carbon of our alkyl halide and kick out bromide as a leaving group. Now we're going to need access to an ether, but this time it's not a symmetric ether. We have two different groups on the left and right. We made an asymmetric ether. So you can see immediately the Williamson ether synthesis is far more applicable to fine chemical synthesis. An industrial chemist would hate this reaction. First of all, it's multiple steps. So you have to first add the sodium hydride and then add the alkyl halide, whereas an industrial chemist would prefer to just mix all the components together in a giant vat and then come back a few hours later with tons of product. Right? This is going to require the fine hand of a chemist to control each step and monitor each step. Also, the first step is typically done at reduced temperatures, so the chemist is going to have to cool the reaction down. You can imagine at an industrial scale, cooling down a multi-ton vat of chemicals is going to require a lot of energy at an extremely high cost for that refrigeration. So for that reason, typically, industrial reactions are either done at or slightly above room temperature. Okay, anyway, we digress. The Williamson ether synthesis reaction can occur intramolecularly. What does that mean? Well, it means that if we have a molecule that has an alcohol and an alkyl halide together, when we treat that molecule with sodium hydride, we can trigger an intramolecular Williamson ether synthesis. Intramolecular meaning within the same molecule. So the sodium hydride will do what it normally does, which is deprotonate the alcohol to form the sodium alkoxide. Give us a species shown. And the alcohol is going to act like a nucleophile and attack across itself to kick out bromide as a leaving group. The product is going to be a cyclic ether. And this cyclic ether in particular is THF, which is a solvent that we've seen before in this class. Tetrahydrofuran is what it stands for. And this is an example, it's actually the first example we're seeing of a cyclization reaction. A cyclization reaction is any reaction that produces a ring. How small of a chain can we go? What's the smallest sized ring we can make? Well, it turns out the smallest polygon you can have is a triangle. So the very first thing that chemists would have tried, which is try and make a triangle. Okay. So if we take this alcohol alkyl halide and treat that with sodium hydride, it turns out it works. And we're going to produce, just as usual, our deprotonated sodium alkoxide. Notice I'm not drawing the sodium counterion because it's just going to clutter the screen. That O- is going to attack on itself and kick out bromide. And that's going to give us the 3-membered ring cyclic ether. So this is, again, a cyclization reaction. And this ether is very special and has a very special set of characteristics and engages in a special set of reactions. And we're going to call this ether epoxide. This is an epoxide. It's its own functional group. It's also sometimes called an oxyrane. By the way, these happen to be very high-scoring Scrabble words that will really piss off your friends and family. So be sure to use epoxide or oxyrane in your next Scrabble game. What is so interesting about epoxides is that they're highly reactive. So ethers are normally unreactive. For example, we've seen ethers before in the class. Diethyl ether and THF. Both of these ethers we saw in the context of solvents. And generally speaking, you don't want your solvents to be reactive at all. You want your solvents to simply dissolve all of your starting materials. You don't want any sort of reactivity between the starting materials and the solvent. And so that sort of attests well to the inert characteristics of most ethers. However, epoxides are very reactive. The reason they're so reactive is because of ring strain. If you look at the epoxide, the bonds, which are sp3 hybridized carbon-carbon bonds, are set to 60 degrees, which is far from its ideal bond angle of 109.5. So because of all of this excess bond strain, the epoxide is just ready to bust open. And so as we're going to see, the reactions of epoxides are defined by their desire to burst open. Now let's look at the reactions of epoxides. And these reactions fall under two categories. We have basic ring openings, and we're also going to have acidic ring openings. And sometimes we'll define the basic ring openings as simply not acidic. We're going to take a look at these two types of ring openings in the lecture today. In both of these reactions, the key step is the same, and it's going to involve a nucleophile attacking the epoxide, which is acting as an electrophile. So if we have our epoxide here, it's going to act like our electrophile, and we're going to have some various nucleophiles attacking one of the carbon atoms of the epoxide and then opening the ring. And we'll find that the conditions that we use are going to affect the regiochemistry and mechanism. Okay. Let's begin by looking at base conditions. In basic conditions, we're going to be looking for anionic nucleophiles and the absence of acid. The mechanism is going to be ring opening by SN2 followed by protonation. So let's take a look at an example. Here we have an epoxide. I'll put some methyl groups on it. And now let's add a nucleophile. So let's add a great basic nucleophile. That's going to be a nucleophile with a negative charge. So how about ETO minus? That nucleophile is going to attack the less substituted side of the epoxide because it's an SN2 reaction, and we know that SN2 reactions are very sensitive to substrate sterics. So we're much going to prefer to attack the primary carbon of the epoxide rather than the right tertiary carbon. It's going to kick electrons up onto oxygen. Sort of we have this O minus acting as a leaving group, and we've seen before that O minus is not a good leaving group. But because of the ring strain, it's willing to act like a leaving group. Now if we draw the product of that reaction, we can see that we've added our ETO to the carbon. And now we have an O minus, or an alkoxide. Okay. Then in step 2, we're going to need to add water as a workup. So here's some H2O. And our alkoxide is going to attack the H of the water, kick electrons onto oxygen. And now we're going to have a alcohol as the product. So whenever you do a base or acid catalyzed ring opening of epoxide, you're going to find that your product is always an alcohol. So this is another way to make alcohols with the nucleophile substituted to the beta position. In other words, the product of epoxide ring opening is a beta nucleophile substituted alcohol. In terms of regioselectivity, the reaction is regioselective, and it favors attack at the less substituted side. The reaction is also stereoselective, and there will be inversion at the site of attack. Okay, so now we're going to look at some more examples of how stereochemistry is affected in these reactions. So the example we looked at, our ethoxide ion was not attacking a chiral carbon, so we didn't get to see the fun effects of inversion. So let's look at another example where inversion will play a bigger role. So for that, we'll need to make a nice chiral epoxide. And so I'll put some substituents on my epoxide. I'll put a methyl group and an ethyl group on the right. And then on the left, I'll put a methyl group and a hydrogen. All right, now we'll need to add a good basic nucleophile. So let's see. For these reaction conditions, I'm going to use step 1, NaSH. That's a good anionic sulfur. That's a very good nucleophile. And then in step 2, of course, I need my H2O workup. So I'll go ahead and add that. And so here's my nucleophile, SH. And so since this is basic conditions, the nucleophile is going to attack at the less substituted side of the epoxide. Spoiler alert, when we get to the acidic conditions, it's going to attack the more substituted side, but we're not there yet. Okay, so here comes our nucleophile, and it's going to attack the less substituted side, and that's going to kick electrons up onto oxygen. And so now what's going to happen is the sulfur is attacking anti to the oxygen. In other words, sulfur is performing backside attack. So the way that we can draw the product is as follows. Where the sulfur and the oxygen are now anti to one another, but now we need to flip the stereochemistry at the site of attack. So what we're going to do is we're going to flip the methyl group up, and we're also going to flip the H up. Now, this is a common point of contention for a lot of students who say, hey, look at this carbon. The methyl is a wedge, and then in the product, the methyl is still a wedge, and you're trying to tell me that's inversion? And what I'm trying to tell you is, yes, it is inversion, because we are flipping those two substituents up past the horizon. And when I say horizon, I mean this bottom of the epoxide. Imagine the bottom of the epoxide is like the horizon, and this oxygen of the epoxide is like the moon or the sun, right, which is above the horizon. Now look at the substituents on this carbon before the reaction. they're both below the horizon. Well, this H I kind of drew kind of in line of the horizon, but they're supposed to be drawn both below the horizon. And now look at where they are in the product. They're both above the horizon. That is considered an inversion. Okay? So just keep in mind that that is an inversion. So when you do these epoxide ring openings, don't flip the wedges and dashes. Simply rotate the groups upward. Okay? Notice on the right side, the two groups stayed below the horizon. Okay, now we do need to finish our mechanism here by finishing the workup. So we're going to have the water come in and deliver that final proton. And that leads us to our final product. Beautiful. Let's take a look at another example. Now what happens if I have an epoxide that's connected to a cyclohexane ring? This is something that occurs quite often. So we can have something like this epoxide. And then let's treat this one with sodium azide, which is a good nucleophile for SN2. And of course we'll need our water workup. And so let's try and draw the mechanism for this reaction. So when you have the epoxide in the ring, it's a little funky because now you see instead of the oxygen being flat with the epoxide and the substituents being wedged and dashed, kind of like above here, see how the oxygen epoxide was flat and the substituents were wedges and dashes? Now look, the ring is completely flat and the oxygen of the epoxide is on double wedge. Okay. That's a little bit of a weird convention, but the reason that's done is because otherwise you're going to have to put wedges and dashes in the ring, and that's typically not done. So what I like to do to visualize this is try and get a side-on view of what this ring looks like. So let's imagine we're sort of looking at this ring from a side angle. Okay, so like imagine our eyeball was from the side, and what we would see is the epoxide looks kind of like that. And we also have a methyl group that's going down on that position. Okay, so you can see the epoxide's going up and the methyl group's going down. And so now here, let's add our nucleophile N3-. And that's going to attack the less substituted side of the epoxide and kick electrons up on oxygen. So if we do that, we can see now sort of popped open our epoxide, right? There it is, the O- there. And we can see that our azide, our N3, attacked opposite the oxygen. Okay. So now we're going to go ahead and protonate with H2O. This is part of our workup step in step 2. Okay, and then that's going to give us our protonated alcohol. There we have it. And now let's go ahead and translate this back into the two-dimensional drawing. So imagine we're looking at it from above now. What's that going to look like? That's supposed to be an eyeball up there. Well, we see that we have the OH group coming out of the page towards us, and the methyl group is going back. And then our N3 group is going down. Okay, so that's going to be translating the product back. So let's take a look at some nucleophiles that are commonly used in basic conditions. Oh, yeah, so just up here, I'll go ahead and just draw the product again. Just so we can complete our scheme. And so some nucleophiles that are used in basic conditions, they kind of come into two categories with epoxides. There are your standard nucleophiles that do SN2 reactions too. So I'll call those normal SN2 nucleophiles. And here's a list of some normal SN2 nucleophiles. You could have things like deprotonated sulfur anions, deprotonated oxygen anions, deprotonated nitrogen anions. We could even have things like cyanide or deprotonated alkyne. And we're also going to have some special nucleophiles that work with epoxides but don't work usually with SN2. So I'll call these special nucleophiles. And these nucleophiles, no SN2, so don't ever try to use these in SN2, but epoxides are okay. And some special nucleophiles could be, for example, LiAlH4, which is a source of H-, or organometallics like Grignards and organolithiums. Okay. Of course, these two are going to be a source of C-. Okie dokie. So these are some wonderful nucleophiles. Well, let's go on and talk about acidic conditions. So now you pretty much know what you need to know about basic conditions. In acidic conditions, we're again going to be starting off with an epoxide. And this time the reagents are a little bit different. Instead of treating it in step 1 with a strong anionic nucleophile, we're going to treat it in step 1 with H2SO4, all in one step, by the way. With acidic conditions, you don't have 2 steps. It's all a one-step process. We're going to add H2SO4 and then some nucleophile of our choice that's typically neutral. So I'll represent a neutral nucleophile by showing it connected to an H atom. And then the product of this reaction, again, is going to be an alcohol, but this time the nucleophile will be attacking at the more substituted side. I kind of alluded to that earlier. So for this reaction, we're going to want to use a neutral nucleophile. Use a neutral nucleophile. And the reason we're using a neutral nucleophile is we're in acidic conditions. So if we even try to use an anionic nucleophile, it would probably just do an acid-base reaction with H2SO4 anyway. And notice that the nucleophile now is attacking at the more substituted side. Let's take a look at the mechanism of this reaction. And just so you know, I typically do put this mechanism on exams. So the mechanism of the reaction begins with protonation of the epoxide itself. So let's go ahead and give us a nice chiral epoxide this time so we can look at the stereochemical impact. So the first step is going to be protonation. So we do have that sulfuric acid there. So in step 1, the sulfuric acid is going to act as a proton source for our epoxide. Okay, so here comes our lone pairs on the epoxide are going to grab a proton from the sulfuric acid. And that's going to give us a protonated epoxide. Protonated epoxides are extremely, extremely reactive. And it makes sense that the protonated epoxide would be reactive because now not only do you still have the ring strain of all these bonds being contorted into this far from ideal 60-degree bond angle, but also now the oxygen's not a bad leaving group. Before, the oxygen was a really bad leaving group, but now the oxygen's a good leaving group too. So we'll just say epoxide with positive charge is good electrophile. Really good electrophile. Step 2 of the mechanism is that our neutral nucleophile is going to come along and it's going to attack at the more substituted side. So here comes our methanol. It's going to attack at the more substituted side, and just as before, we're going to be breaking open that epoxide, kicking electrons onto oxygen. Okay, so let's see what that produces. This is going to give us an alcohol as the product. And again, we're going to see inversion of the stereocenter. So I'm going to flip up the ethyl, and our methyl group are going to get flipped up, and that's going to be considered an inversion because they cross that horizon line. And now we're going to have the methanol again could come back and act as a base, or we could just use a generic base, which is going to do the last step of the mechanism, which is acid-base reaction to neutralize the product. So this was nucleophilic attack was step 2. And then step 3, acid-base. And so that's going to lead to our final product, which again is the beta nucleophile substituted alcohol. The big difference here being that under acidic conditions, our nucleophiles attacking from the more substituted side. And again, you can use a generic base here, or you could use another molecule of the methanol as your base. Take a look at another example here. We can take an epoxide and treat it with HBr and also do an acidic ring opening of the epoxide. So you can use HBr as the sole reagent. Okay. Let's take a look at what that would look like. So again, we could have our epoxide connected to a cyclohexane. Okay. And then let's go ahead and treat that with just HBr. And what we'll find the product of this reaction is as follows. Looks like this. Let's take a look at the mechanism. So, mechanism is pretty much exactly the same as what we saw in the previous slide. So we have our epoxide. And in step 1, it's going to undergo protonation. And this time our acid is not H2SO4, but HBr. So our epoxide is going to get protonated by the strong acid, HBr, and that's going to give us a protonated epoxide. And protonated epoxide is a really good electrophile. It's just ready to burst open. So now our nucleophile, which is Br-, which was generated by the HBr. So we have a really good electrophile, and we have a good nucleophile Br- in this case. And that is going to attack the more substitute side, because again, we're still under acidic manifold here. And that's going to open up the epoxide. So I could go ahead and I could draw the sort of three-dimensional side-on view of this. So I'll do that for you now. So here's our cyclohexane epoxide going up, and it has a little H on it, I guess, and a plus charge. And then we also going to have a methyl group that's going down, and then our Br- is attacking that epoxide at the more substituted side and kicking electrons on oxygen. So that's what's happening, and so you can see in the product, hopefully you can see for yourself without having to draw this 2D structure, the 3D side-on view, which is taking a lot more time to draw than the 2D structure, that the product is going to look like this, where the bromine came in from the bottom. The methyl group gets pushed down up, since we do have to do that inversion and push that methyl group past the horizon. Right? You can see this methyl group here is going to be pushed past the horizon. And then we're going to have our oxygen going up as well. Okay, so that's how we're going to get to that product. So in terms of the stereoselectivity, the reaction occurs with inversion just like in the basic conditions. So inversion at site of attack. So whether it's acidic or basic conditions, you're always going to have inversion at site of attack. And we see that in the example above, how that methyl group got inverted because the bromide attacked that carbon. In the regiochemistry, we're going to be attacking the more substituted carbon. In acidic conditions, nucleophile attacks the more substituted side. Okay, and let's kind of give a little explanation of why, and we're going to use a bit of an SN1 type reasoning. Okay, so if we have an epoxide that's protonated, I'll put two different substituents on it. It turns out this epoxide is sort of almost opening up on its own before the nucleophile even gets there, similar to an SN1 reaction where the leaving group would dissociate to give a carbocation, but we know that we're not truly forming a carbocation because if that was the case, we would lose all stereochemistry and we would get racemic products, but we do know that we do have some stereochemistry. In particular, we're getting inversion. That tells us we're not going through a true, pure carbocation. So this, though, looks more like this, where we're sort of generating a partial positive charge because the epoxide's sort of busting open on its own. And so it's going to be generating a strong partial positive charge on the carbon that's better able to tolerate it. On the more substituted carbon, you have better stabilization of that plus charge, similar to how a tertiary carbocation is more stable than a primary carbocation. So you can see that we do have these partial charges on both the left and the right, and then the right side is going to have a greater partial positive charge because that's a more stable position for that partial positive charge. So then when we have a nucleophile come along, it's going to want to attack the more substituted side, since that side is more partially positive, and our nucleophile, of course, is partially negative. So that's the reasoning. All right, let's take all this into a synthesis problem, and then we'll finish up. So let's make this aldehyde from this epoxide. Okay, so to solve this problem, let's do a retrosynthesis. And if you want to try and solve it on your own, go ahead and pause the video right now, and you can give it a try on your own. But we're going to go ahead and solve it. So starting from our aldehyde, let's do a retrosynthesis. We only know really one reaction that makes aldehydes, and that is the PCC reaction on primary alcohols. So if we go back one step, that aldehyde could be made from the PCC oxidation of this primary alcohol. And if we look at that product, that's a beta nucleophile substituted alcohol. We could make that from an epoxide. This is a very easy synthesis. This is the power of epoxides, allows us to build up a great deal of complexity in very few steps. So starting from our epoxide, let's go through the forward synthesis. We can treat that with, well, we need to open the epoxide from the more substituted side with chloride. So to do that, we'll add HCl. That's acidic ring opening, and our nucleophile is chloride. So that's going to go ahead and give us the chlorine adding to the more substituted side. And then we're just going to treat that with PCC, and that's going to lead us to our aldehyde. Typically, it's pretty easy to spot when epoxides are used in synthesis problems, and so my secret is to look for two heteroatoms on adjacent carbons. So this is my secret. Look for two heteroatoms on adjacent carbons. For example, right here we have a heteroatom on these two adjacent carbons. Another example. Again, 2 heteroatoms on adjacent carbons. And we could even have a bridged bicyclic molecule here. Again, all 4 of these compounds could be made from epoxides, and so the secret is noticing that all of them have this in common, where they have 2 heteroatoms on adjacent carbons. Okay, so that's pretty much what you need to know about ethers and epoxides. And so the key, though, of course, is going to be doing lots of practice problems so they get comfortable with all the nuances and details of these reactions. Really, the challenges come in 2 forms. The first challenge being the stereochemistry, and oftentimes students getting confused with how to draw the inversion products of epoxide ring opening and whether they're supposed to flip the wedges or dashes or just flip them above the horizon. I think that's a point of confusion, and with a few practice problems, I think you'll nail that. And then the other source of confusion is that there is really a wide diversity of nucleophiles that can be used, and there's typically an acidic and a basic version of each nucleophile. For example, if you wanted to open an epoxide under basic conditions with OH versus acidic conditions with OH, you would use NaOH to open an epoxide with basic conditions. So that would be step 1 NaOH, step 2 H2O for the workup. Whereas in acidic conditions, you would do H2SO4 and water. Let's look at another example. What if you wanted to open up an epoxide with, how about an alcohol? You could use KOMe, potassium methoxide, step 2 H2O if you wanted to do basic conditions. And then under acidic conditions, you could do H2SO4 and MeOH. Another example. Let's say you wanted to open an epoxide from the less substituted side with a halogen. You could treat that in step 1 with NaI, step 2 H2O. And then if you want to do that in acidic conditions, you would just treat it with HI. Okay. So you can see there's some challenges there associated with which nucleophile to choose depending on whether you want that nucleophile to attack the more or less substituted side. Okay, that's it for now. So we're going to talk more about epoxides, and we're going to dive into a new class of reactions, alkenes and alkynes, coming up soon.